Precipitation. Mean precipitation over an area, depth area duration relationships. Reported by Christine Jewel H. Silvano, Year and Section DSCE 3A. For the first topic, we will discuss mean precipitation over an area. Rain gauges represent only point sampling of the areal distribution of a storm. In practice, however, hydrological analysis requires a knowledge of the rainfall over an area, such as overcatchment. There are three methods that is used under mean precipitation over an area. We have first arithmetical mean method, second Thiessen-Polygon Method, and the third one isohyetal method. In arithmetical mean method, when the rainfall measured at various stations in a catchment show little variation, the average precipitation over the catchment area is taken as the arithmetic mean of the station values. Here is the formula for the arithmetical mean method. Average rainfall is equal to the rainfall measured in station 1 plus the average rainfall measured in station 2 plus P sub I up to P sub n all over n, where n is the number of stations. So, as the name suggests, arithmetical mean method is just the summation of the different measurements taken from different rain stations and divided by the total number of rain stations over a catchment area. Next, we have Thiessen-Polygon Method. In this method, the rainfall recorded at each station is given a weightage on the basis of an area closest to the station. Thiessen-Polygon Method. Thiessen polygons are the bounding polygons formed by the perpendicular bisectors of the lines joining nearby stations. To get a better idea of what Thiessen polygons are, let's consider this figure of a catchment, where the points here are the rain stations. As you can see, only 3 of the 6 stations are within the boundary of the catchment, while the other 3, namely Station 3, Station 5, and Station 6, are outside the catchment area. Then, we will draw lines connecting the points of the station, forming triangles. And then, we will locate the bisectors of each side of the triangles. Then we will connect the points of the bisectors, forming polygons. Here in this table is the tabulated values of the polygons and their corresponding station and their corresponding area. For polygon bounded by A, B, C, D, the area is A sub 1 and the station is station 1. For the area bounded by K, A, D, E, we have area A sub 2 and the station 2. The polygon EDCGF has an area A sub 3 and its corresponding station is station 3. The polygon FGH has an area A sub 4 and its station is station 4. And so on. As you can see, polygon ECF, EDCGF, and polygon HGCBJ and polygon JBAK has their station outside the catchment area. However, the reason why these stations corresponds to them is because these stations are the ones closest to them. A is the total catchment area. Here is the formula for the Thiessen-Polygon Method, where the average rainfall over the catchment area is equal to P sub 1 times A sub 1 plus P sub 2 times A sub 2 up to the nth term all over the total catchment area, or summation of the areas of the Thiessen polygons. Thus, in general form, for M stations, P sub bar, or the average rainfall, is measured or equal to the summation of P sub I times A sub I all over A, where the P bar is equal to the average rainfall over the catchment, A sub I the respective area of the Thiessen polygon, P sub I is the rainfall magnitude recorded by the station of a Thiessen polygon, and A is the total catchment area. The ratio A sub I all over A is called the weightage factor for each station. Example 2.5. In a catchment area approximated by a circle of diameter 100 kilometers, 4 rainfall stations are situated inside the catchment, and 1 station is outside in its neighborhood. The coordinates of the center of the catchment and of the 5 stations are given below. Also given are the annual precipitation recorded by the 5 stations in 1980. Determine the average annual precipitation by the Thiessen-Mean Method. So from the given, the center of the catchment area is located at 100 and 100. 100 kilometers away from the origin to the left of the origin, and 100 kilometers above the origin or starting point, and it has a diameter of 100 kilometers. So from the table we can determine the location of each station, and here is the graph. So the solution is, the catchment area is drawn to scale and the stations are marked on it. The stations are joined to form a set of triangles, and the perpendicular bisector of each side is then drawn. The Thiessen polygon area enclosing each station is then identified. It may be noted that Station 1 in this problem does not have any area of influence in the catchment. The areas of various Thiessen polygons are determined either by a planimeter or by placing an overlay grid. So for Station 1, it doesn't have any area covered, so we'll move on to Station 2. Station 2 is bounded by the polygon ABCD, colored in green. Its area is 2,141 square kilometers. Station 3 is bounded within the polygon DCE and has an area of 1,609 square kilometers. Station 4 is within the boundary of polygon ECBF, colored in pink, and has an area of 2,141 square kilometers. And finally, FBA, which has a area of 1,963 square kilometers, and its corresponding station is Station 5. And then to get the weighted area or the values for the fourth column in this table, we will only divide the area of each polygon from the total catchment area. So for polygon ABCD, we will divide 2,141 by 7,854 to get 0.2726, and we'll do that for the following polygons. And as we summed up all the fraction of total area, it must be equal to 1. And the weighted P of each polygon can be calculated by multiplying the average measured rainfall to its corresponding area. So for polygon ABCD, the recorded rainfall is 135.2 centimeters, and we're gonna multiply that by 0.2726 to get 36.86. And for polygon DCE or area DCE, we have 0.2049 fraction of total area, and we're gonna multiply that by 95.3, which is the recorded average rainfall of station 3, to get 19.53. And we'll just do the same calculation for the remaining polygons to get the answers listed in the table. So to get the mean precipitation, we're just gonna add up all the values in the fifth column to get the answer, 121.84 centimeters. So the third method in this topic, mean precipitation over an area, is the isohyetal method. An isohyet is a line joining points of equal rainfall magnitude. In the isohyetal method, the catchment area is drawn to scale and the rain gauge stations are marked. So from the figure, as you can see, the isohyets here are the lines. Crossing the catchment area. Since these lines, the rainfall magnitude over these lines are equal. The recorded value for which aerial average P sub bar is to be determined are then marked on the plot at appropriate stations. Neighboring stations outside the catchment are also considered. The isohyets of various values are then drawn by considering point rainfall as guides and interpolating between them by the eye. The area between two adjacent isohyets are then determined with a planimeter. If the isohyets go out of catchment, the catchment boundary is used as the bounding line. The average value of the rainfall indicated by two isohyets is assumed to be acting over the inter-isohyet area. When we say inter-isohyet area, it is the area between two isohyets. Thus, P sub 1, P sub 2, up to P sub n are the values of isohyets, and if A sub 1, A sub 2, up to A sub n-1 are the inter-isohyet areas respectively, then the mean precipitation over the catchment of area is given by A sub 1 times P sub 1, the quantity, A sub 1 times the quantity of P sub 1 plus P sub 2 divided by 2 plus A sub 2 times the quantity P sub 2 plus P sub 3 all over 2, and so on, until the nth term all over the total catchment area. The isohyet method is superior to the other two methods, especially when stations are large in number. So, example problem for isohyetal methods. The isohyets due to a storm in a catchment were drawn, and the area of the catchment bounded by isohyets were tabulated as below. So for our for our area 1, which is colored in yellow, the average value of P is equal to 12, which is also the value of its isohyet. And for the second area, colored in green, we have an area equal to 140 square kilometers, and the isohyets that bounds it are in magnitude of 12 and 10. Averaging the two values, we will get 11. Next, we have the area bounded by the isohyoids with a magnitude of 10 and 8 respectively. This third area has an area of 80 square kilometers. The average value of 10 and 8 is 9. And we'll do the same method to the rest of the areas. As you can see pala sa area na colored in red, bounded siya ng 2 isohyoids na 6 at 4. Pero, yung area na consider natin is yung hanggang sa catchment area lang. Kasi, yung catchment area, ang magsisilbing boundary, hindi siya pwedeng na magpass sa catchment area. Kaya, ang area na in red is bounded by the isohyoid with magnitude of 6 and the catchment boundary itself. Okay. Ngayon, yung fraction of total area, same procedure pa rin. Para sa area in yellow, i-divide lang yung area ng yellow sa total area ng catchment. So, 30 divided by 450 will get 0.0667. At saka para naman sa area in green, yung meron siyang area na 140 square kilometers. I-divide lang yon sa total area na 450 and we will get 0.311. And then for the area in pink, which has an area of 80 square kilometers, i-divide lang sa total area na 450 square kilometers. Kukuha natin ang 0.1778. Sa area naman in orange na merong saklaw na 180 square kilometers, i-divide lang yan sa 450 and we will get a value of 0.4000. At saka sa area naman in red na may area na 20 square kilometers, i-divide lang yan sa 450 square kilometers and we will get 0.0444. Okay. And then, syempre, yung summation ng fraction of total area must be always equal to 1 or 100%. Okay, sa fifth column naman nakalagay ang ating mga corresponding weighted P for each polygon. So, for the area in yellow, i-multiply lang ang value ng column 2 sa column 4. Or in short, i-multiply lang natin yung corresponding value ng P sa corresponding fraction of total area nito or the weighted area. So, 12 times 0.667 is equal to 0.800. Tsaka para naman sa area in green, 11 times 0.311 is equal to 3.422. And we'll do the same process for the rest of the polygons. So, summing up the values of the weighted P in the fifth column, we will get the average rainfall for the catchment area, which is equal to 8.844 centimeters. Depth area duration relationships. The areal distribution of characteristics of a storm of given duration is reflected in its depth area relationship. A few aspects of the interdependency of depth, area, and duration of storms will be discussed. Depth area relation. For a rainfall of a given duration, the average depth decreases with the area in an exponential fashion given by P sub bar is equal to P sub naught times the natural number raised to negative k raised to the number quantity negative k times a raised to n, where P sub bar is the average depth in centimeter over an area A in square kilometers, and P sub naught is the highest amount of rainfall in centimeters at the storm center, and K and N are constants for a given region. So K and N varies and depends on the place being considered. Here is an example of a tabulated value for K and N. On the basis of 42 severe-most storms in North India, Dar and Bhattacharya, in 1975, they have obtained the following values for K and N for storms of different duration. So as you can see, on the first day, the value of K and N is the values of K is the least, while the value of N is the greatest. On the third day, the value of K has increased, while the value of N has decreased. Since it is very unlikely that the storm center coincides over a rain gauge station, the exact determination of P sub naught is not possible. Hence, in the analysis of large area storms, the highest station rainfall is taken as the average depth over an area of 25 square kilometers. Maximum depth area duration curves. In many hydrological studies involving estimation of severe floods, it is necessary to have information on the amount of rainfall of various durations occurring various sizes of areas. The development of relationship between maximum depth area duration for a region is known as DAD analysis and forms as important aspect of hydrometeorological study. A brief description of the analysis of DAD curves. First, the severe-most rainstorms that have occurred in the region under question are considered. Second, isohyoidal maps and mass curves of the storm are compiled. Third, a depth area curve of a given duration of the storm is prepared. And lastly, then from a study of the mass curve of rainfall, various durations and the maximum depth of rainfall in these durations are noted. The maximum depth area curve for a given duration D is prepared by assuming the area distribution of rainfall for smaller duration to be similar to the total storm. The procedure is then repeated for different storms and the envelope curve of maximum depth area duration D is obtained. So sa paghanap ng maximum depth area curve, hindi naman kailangang i-consider yung kabuuhang area na merong bagyo. Makuha lang doon ang part ng catchment sa area na yon para masukat yung depth area curve. So small area lang ang tsaka smaller duration lang pala ang ang i-consider. So for example, ang tinagal ng storm ay 10 hours. Pwedeng mas mababa pa sa 10 hours ang kunin na duration para makuha or masukat yung depth area curve. So here is an example of maximum depth area duration curves. As you can see or as you can notice, yung maximum average depth is inversely proportional sa area. So kapag tumataas yung area, mas mataas yung area, bumababa din yung maximum average depth. However, the depth is directly proportional to duration. Here is another example of tabulated values in table 2.3, maximum observed rain depths in centimeter over plains of North India. That's all for my report. Thank you.